Hello everyone. Today we're going to continue our discussion on vector space, and if I remember correctly, yesterday we defined something called subspace. So the concept of a subspace is basically taking a larger vector space and try to just pull out a smaller subset of the element from the larger vector space. And the idea is that so that we can kind of not necessarily have to talk about a really large vector space if we don't need to talk about it, and show you some example of some subspace and hopefully give you a better understanding on how this works. So imagine the following. So let's talk about a very simple example. Let's say in R3, let's consider all vectors in the form of x, y, 0. And so if you think about it, so this basically just define all vectors that have a 0 as the z coordinate. So therefore, if you think about it geometrically, this basically represents the xy plane in our xyz space. So let V be the set of all vectors in the form of x, y, 0. What I want to do is to show V is a subspace of R3. You will be asked to do a problem similar to this on your next test, is to try to show that a given subset of a larger vector space would form a subspace. So how do we actually do that? So the key is to prove the three properties that we need to have: addition closure and scalar multiplication closure. And then also, by doing so, we still include the 0 elements within our subspace. So let's go and try this. So the way to prove that is to simply show that those three properties exist. So the easiest one to show is this one, would be the 0 vector. So in this case, we're going to say that the 0 vector will just be 0, 0, 0, which is definitely in the subset of V, because it would be in the form of x, y, 0, where x and y are both 0 in this case for the 0 vector. And let's try to prove the addition closure property and the scalar closure property. So to do that, I have to first define two elements, and we'll call vector v and vector u to be in the set of V. And so here's the important part, is that then you have to define, like, what does that mean when I say vector u and vector v are both in the set V? Well, that would imply that vector u must be in the form of u1, u2, but has to have a 0 on the third coordinates. And vector v can have a number v1, v2, but has to have a 0 in the third coordinate also. So now the question is, if I now add these two vectors together, what would happen? So what we want to show is that if I add these two vectors together, the result would still be within this set, meaning that the result would have maybe two different numbers in the first and the second spot, but it has to have a 0 in the third spot, because every element in V must have a 0 in the third spot. So, and you can probably see that it would be true, because you're basically doing this. You'll do u1, u2, 0, plus v1, v2, 0, and therefore become u1 plus v1, u2 plus v2, and then 0 plus 0 would still be 0. So therefore, this vector would have to be in V, because it's exactly the same as this vector, except that in this case, this vector has a specific x value, which is u1 plus u2, and a specific y value, which is u2 plus v2. So this vector would have to be in V. It didn't form some kind of different vectors from it. And let's say we take a scalar and multiply by vector u, what would happen? So it would be s times u1, u2, 0, and therefore become su1, su2, 0. And notice that the third coordinate remains 0 in this case, while the first two can be anything. So once again, this is exactly the same as this vector, except that we have a specific x value of SU1 and specific y value SU2, but the third coordinate still remains 0 in this case. So therefore, this vector is also in V. So therefore, we show the 0 vector. Here we have the closure for vector addition. And here we have the scalar multiplication closure. So therefore, after you show these three things, you can now say that V is a subspace of R3. So on your test, that is exactly how you're going to proceed. On your test, let me maybe title this one. This would be a closure for addition. And this is closure, oops, for scalar multiplication. Okay, kind of squeeze it in. Okay, so you basically do exactly the same thing on your test when you're being asked to show something is a subspace, is by first identify the 0 elements, make sure the 0 element is still within your set. So therefore, whatever condition that the problem defined, you have to make sure that this 0 vector will work. And of course, here you have to also think about what should be the 0 vector for the original vector space. So for R3, the 0 vector will be 0, 0, 0. So for some other vector spaces, it could be different, meaning if it's for the polynomial space or continuous function space, you will call the 0 vector the function 0. And then you have to make sure that that is still satisfy whatever condition that the problem defined. And if it's a matrix space, you have to make sure that you have the 0 matrix. Okay, and then next, to prove the closure and property for both addition and scalar multiplication, you have to define two elements within your set, and then you have to basically write out what does that mean when you say those two are element within the set. Okay, in this case, it will mean that the two vectors u and v will have to be in this form. And then you try to add and try to multiply one of them by scalar, and to hopefully show that the result after you do it remain the same form, that's the same property, define the subset. In this case, define the subset is that they have a third number that's 0. And that complete your proof. Now I'll show you a different one that illustrates similar concepts. So let's see. So here we go. Second example. And we'll go through the same exact thing. Second example. So consider the polynomial, say, the polynomial space P sub 2. So what is P sub 2? So that means in P2, P sub 2, the polynomial space of all polynomials of degree 2 or less. Consider, oops, all polynomials in P2 that are in the form of let me write a second line. P of x equal to a sub 0 plus a1x. So essentially, I'm asking you to consider all the polynomial of degree 2 or less, so meaning all the polynomial that are quadratic or less. And I'm looking for a subset that are linear within that quadratic vector space. So this P sub 2 can be thought of as the quadratic polynomial vector space. And now I'm looking for the subset within that quadratic polynomial vector space that are linear polynomials. And I want to ask you to show that it is a subspace. So we're going to go ahead and let V be the set of all polynomials P of x equal to a sub 0 plus a1x. And I'm going to ask you to go and show V is a subspace of P2. Okay? So how do we proceed? Well, same way as before, what we're going to try to do is several things, and if you want to list them for yourself, you should. First, make sure that the 0 element still remain within this subset. Number 2, define 2 elements within this subset, and then try to add them and show that the sum remain within this subset. And then try to multiply one of those 2 elements you define by a scalar and show that the result remain within the subset. And if you can do all that, then you have a subspace. If any one of those fail, you don't have a subspace. So let's start with the following. Let's start with the 0 elements. So is our 0 element exists in our subset? So, well, let's see. So we call the 0 element in a polynomial space is z of x equal to 0. Which, if you think about it, that just basically meaning 0 plus 0x. And therefore, it definitely is in the form of the polynomial that we want to define, with a specific a sub 0 value to be 0 and specific a1 value to be 0. Therefore, it is in our set of V, because in the form of a sub 0 plus a1x. In our case, 0 plus 0x. 2, we're going to define 2 elements. So I'm going to go and let P of x and Q of x be in V. So now what does that mean? Well, that would mean that P of x must equal to a sub 0 plus a1x, and Q of x must be equal to b sub 0 plus b1x. You don't have to use a sub 0, a sub 1, b sub 0, b sub 1. You can use some other letter with some other subscript. However, I do recommend to use subscript 0 and 1 just to be consistent with the way that the problem define the property of what element within V. Okay, but you can definitely use different letters. I just like to use A and B. So if I have these 2 elements within P, I want to show if I add them together, the sum will still look the same. So let's give it a try. So I'm going to go ahead and try to do the addition, closure. So what if I add P and Q together? Well, that would just mean a sub 0 plus a1x plus b sub 0 plus b1x. And so what I'm going to do is I'm going to try to combine line terms together and say, oh, that's just a sub 0 plus b sub 0 plus oh, sorry. I was thinking b already while I'm trying to write a sub 1 plus b sub 1 x. So now, is that in our set V? Well, of course it is. So if I compare this expression to this one, that just basically tells me that this is like my a sub 0 right here, and this is just my a sub 1 right there. So therefore, this is still in the same form as what we want in V. You still have a linear polynomial. So it's close. And now let's talk about closure for scalar multiplication. Oops. So if I take a scalar s and multiply by p of x, what will happen? Well, that would be s times a sub 0 plus a1x. So if I distribute the s, I'll have a sub 0s plus a sub 1. Or actually, maybe I should write it this way. Okay, maybe I should write it this way. S a sub 0 plus s a sub 1x. So therefore, this s a sub 0 become my new a sub 0, and then s a sub 1 become my a sub 1. Notice that this is still just a linear polynomial, just like which is what every polynomial in V would be, a linear polynomial. So this would still be V. And therefore, by showing that the 0 element is in V, and addition closure and scalar multiplication closure both are satisfied, I can now conclude that V is a subspace of P2. Now, I'm hoping that when I go through this particular example, some of you recognize something very familiar. And some of you might even have a little deja vu, and you should, because the entire problem that we just did is the same exact problem that we did right here. And some of you probably recognize the similarity or the parallel between these two examples because they actually are exactly the same. How? Well, show you. And hopefully by showing you this, help you understand what we are trying to do by defining something called vector space. So compare these two examples. I notice the following similarity between them. In the first example, we are doing something in R3. So therefore, you can think of it as the vector xyz. And then V consists of only element that xy0. Okay? Now consider what happened in P2. So P2 would consist of every polynomial in the form of P of x equal to a sub 0 plus a1x plus a2x squared. And our V in this case will consist of every polynomial in the form of a sub, jumped the gun here. Every polynomial in the form of a sub 0 plus a1x. Now, how could these two be parallel? Well, if you think about it, P2, I'll basically just talk about these three coefficients in the polynomial, because every single polynomial that's degrees 2 or less are defined basically by these three coefficients. So therefore, you can think of this as just a vector a sub 0, a sub 1, a sub 2. Or, I mean, look pretty much the same as xyz, except I call them with different name. And then this vector v right here would define by just a sub 0 plus a sub 1x, which effectively saying that a sub 2 must always be 0 for this to work. And therefore, telling me that we are basically considering the vector a sub 0, a sub 1, 0 as our v. And now, hopefully you can see the similarity between these two. As a matter of fact, from a mathematical standpoint, these two examples are exactly the same. Now, which come to something very important that I want you to understand about why we are talking about vector spaces. The idea is the following, is to kind of have a visualization of some of these vectors and how they combine together. And if you think about it, look at what happened on this side. R3 is considered to be a three-dimensional space, like XYZ space. And guess what V graphically represent? It represents the XY plane in R3. Because the first two coordinates and then 0. While in our case right here, P sub 2 represent polynomial of degrees 2 of less or less. But if you think about it, if I simply just look at this polynomial of degrees 2 or less as a vector like this, then it's actually, we can interpret this as a three-dimensional space also. And now here comes the important part. We actually haven't really formally mathematically defined what is dimensions, and we will define that later on in this section, in this chapter 3. Okay, but intuitively you understand a three-dimensional space is like the room that we're in. Okay, so have left, right, up, down, forward, and back. So we can now spatially imagine P2, which is just polynomial function, but we can now interpret geometrically as is more similar to a three-dimensional space than anything else. That's the important part that we want to introduce vector space. And that's the reason why I call vector space, because it actually make it geometrically behave more like a space than anything else. So instead of looking at it from an algebraic standpoint, which are just polynomials with variable x, now we can actually visualize them spatially as a space, just like R3. That's important in how we visualize some of the solution that we're going to need to identify and find while we're solving differential equation. So that's the key. And so now we can also imagine that V, which basically are defined to be polynomials, in the form of p of x equal to a sub 0 plus a1x. Instead of think of this polynomial as linear function, we can actually now imagine them to be like the xy plane in R3, where each a sub 0, a sub 1, not only do they correspond to a polynomial function, a linear function, they now also correspond to a point, a position on the xy plane within R3. And now you can visually identify where it is, and now using that visualization to help you understand what's going on. And that's why it's powerful to think of some of these objects as a vector space, as a vector, and how they form a space in a specific dimension. It helps you visualize what they're doing. Now, we'll definitely talk more. We can definitely talk more in class. As a matter of fact, I would like to give you an example for you to try out. As I already told you, you will be asked on your next test to actually prove something is a subspace. So you definitely need to have as much practice as you can. So what I'm going to do is give you another example to try out, so you can see how to show something is a subspace. So this one is actually pretty interesting. We can definitely talk about the geometrical interpretation of what this particular problem asks you to do. Let's say V be the set of all vectors on the plane that satisfy ax plus by plus cz equal to 0 for some constant a, b, and c. Show that V is a subspace of R3. So we are basically saying that V be all a set of x, y, and z that when you plug into this equation, it equal to 0. And a, b, and c are not variable, they're constant. So for some specific a, b, and c. So meaning we could talk about V being a set of all x, y, and z, so that x plus y plus z equal to 0. And in this case, we'll talk about a specific V where a, b, and c are all equal to 1. Or it could be for V being a set of all vectors that satisfy the equation x plus 2 y plus 3z equal to 0. And in that case, we define V to be a vector, a subspace with a being 1, b equal to 2, and c equal to 3. So a, b, and c are constant in this case. That really doesn't matter what they are as long as they don't change. And x, y, and z would be a all number that would make this equal to 0. So I'm going to ask you to try to show that this is a subspace by going through the process that we talk about. And we can definitely go over how to do that in class if you need to. All right. So right now it's 25 minutes into the video. So I just want to maybe talk a few more things, and then we'll end the video. So next thing I want to talk about is theorem. Is this theorem. So theorem 3.2.3. This theorem identifies some common subspaces that we can work with in for Rn. So the subspaces, oops, for Rn are the following. So this lists basically all the subspaces for Rn. Number one, what we call the zero space. And what is a zero space? It's just the subspace that contains only one element, and that element is the zero element. And yes, that would be a subspace because number one, it contains the zero element. Number two, if you take any two elements within the space, which in this case they're only zero vector, so basically you're adding 0 times plus 0, you get 0 vector. And if you multiply 0 vector by any scalar, you get the 0 vector. So therefore, it's definitely additive close and scalar multiplication close, and also contain the 0 element. So it's definitely a subspace. Two, k-plane for k equal to 1 to ... to n minus 1. And all these k-plane must contain the 0 vector. So I don't like the S being all the way out here. Let me just... Okay, there you go. K-planes. And so what is a k-plane? A k-plane basically meaning that you have k dimensional direction vector. So in this case, basically telling me that in Rn, the proper subspace would have to be a plane inside this Rn, but just the plane would have different dimension based on what k is. If you don't remember what k-plane is, you definitely need to look up what you learned in chapter 2 last year. Or just go to your textbook and look up chapter 2, or go to the back and look up k-plane and then go to corresponding section to read up on it. And you definitely have learned what it is. And 3 is Rn itself. As a matter of fact, this gives a very important concept about subspaces that you definitely need to write down for yourself. Is that any vector space is its own subspace by definition. Of course, we don't really want to talk about that because there's no point in talking about a vector space being a subspace of its own. But pure definition standpoint, it has to be true. Okay? And also, with that being said, things that you want to write down for yourself, the 0 space is often referred to as a trivial subspace because it doesn't really do anything, because every vector space would have the 0 subspace, but it just doesn't have anything other than 0 in it. So it's trivial. It doesn't really do anything. And then what happened to the k-plane in this case? The k-plane are often referred to as proper subspace of a vector space, meaning that these are subspaces that are actually smaller than the vector space they came from. And it doesn't just contain the 0 vector, so it contains something more than 0 vector. So they actually have meaning to it. It actually does things. And they are called proper subspaces. Okay? So maybe I should write it down for yourself. The 0 subspace is often called the trivial subspace because it doesn't really do anything, and every vector space has it. And in any vectors, any subspaces, so in this case, meaning the k-planes, other than, oh, I'm sorry, I should say, any subspaces other than Rn, so that refers to all the k-planes, are called proper subspace for Rn. And in general, a proper subspace would be a space that's smaller than the vector space they came from. Okay, I mean, how do I put it? It's contain less element than the proper subspace itself. Have to be a subset of the subspace to begin with, and that's why they call proper subspace, because actually kind of reside within the vector space they come from. All right. Right now it's 30 minutes, so I guess I should stop right here and continue some more tomorrow. All right. So we'll stop right here and continue. We'll talk more about subspaces tomorrow in tomorrow's video. Okay. Talk to you guys later. Bye bye.